Dear students, welcome to the lecture. Today we will discuss about electron spin, and when we observe many spectral line under high resolution spectrophotometer, then we find each line consists of number of very closely spaced uh, lines. And spectral lines are observed due to the transition of electron from one shell to another shell, we normally know. But when we are seeing are two separate lines very close to each other, this is revealing that electron is not only revolving around the nucleus, but it also revolves around its own axis. So it means there is spin of the electron around its own axis. We can take the analogous example for that, as Earth is spinning around its own axis and it is also spinning around the Sun. So Sun is nucleus and Earth is electron. So electron is also revolving around its own axis as well as around the nucleus. And we know each spinning particle causes some magnetic effect. So the spin of the electron around its own axis causes magnetic moment or magnetic momentum. So an electron possesses an intrinsic angular momentum, which is also known as spin angular momentum and designated by capital S vector quantity, and an intrinsic magnetic momentum, it's also known as spin magnetic momentum and designated by mu s due to spin vector quantity. So normally magnitude of the spin angular momentum, capital S bar vector quantity, because this is directional quantity, it would be equal to under root of s into s plus 1 h cross. So here this s small s is the spin quantum number, and in the case of electron spin having the value half s. So if we put the value half s in this expression, we will find capital S var, that is spin angular momentum, it would be equal to half into half plus 1 square root h cross. And on calculating so when we solve this one, we will get here under root 3 by 2 h cross value. So let's take the z component of the spin angular momentum, and we will designate it as capital S z vector quantity. So this is the component of the spin angular momentum along the direction of external field in the space, and this is quantized quantity, a fixed value would be there. So normally the s component the z component of the spin angular momentum, it would be equal to ms h cross. And from the knowledge of quantum numbers, we know this ms is nothing, this is spin magnetic moment quantum number. So normally ms have the value 2s plus 1. So in this case we have s is equal to half. So how many possible values for ms? They would be 2s plus 1. So it would be equal to this is 2 into half plus 1. So 2 cancelled by 2, so it would be 1 plus 1, that is 2. So ms having two possible values. So those possible values would be from minus s to plus s, and we exclude 0 over here. So in this case we ms is equal to plus half and minus half. So plus half mean to say we have up spin, and minus half mean to say down spin. So the spin angular momentum cannot be aligned completely to the applied field. So suppose we are applying the field in z axis, so spin angular momentum, it will not remain completely aligned in the z axis, but can align only in two direction of the z component, and they are plus minus half h cross value. The electron now possesses two intrinsic or internal quantum state for two values of ms, plus half and minus half, and this is only due to the spin of the electron around own axis. So in the next slide, here we are seeing that here electron and it is revolving around its own axis, and this revolution of the electron, it caused the internal or intrinsic momentum. So spin magnetic momentum, last time we have discussed as bar quantity, as vector quantity, and now we will discuss the spin magnetic momentum, that is mu as vector. So how much would be the value for mu as spin magnetic momentum for a given spin angular momentum s bar? So the normal relation is given by mu s is equal to 2 E upon 2m s bar. E is the charge and m is the mass of the electrode. So this capital S bar, this vector quantity, normally this one is equal to s into s plus 1 h cross. We know this one. So if we use this value over here, then we will find this particular value with h cross. And we also know that we are using h cross over here, that is E h cross upon 2m and the square root of s into s plus 1. And normally this quantity E h cross divided by 2m, it would be equal to 4 magneton. So this is written by mu v here. So if we use mu v in this case, then what would be the value for mu s? It would be mu s is equal to 2 into mu v, that is where 4 magneton into s plus 1. So now we can rewrite it as mu s is equal to gs. This is g factor for an electron, and normally this is 2. So we are replacing 2 by this g mu v s into s plus 1 square root. So we also know that s into s plus 1 square root, it could be rewritten by this. If we use this particular formula, then we can rewrite the value for s into s cross. S into s plus 1 square root is equal to s upon h cross. So now we will use this expression over here. So now we will seeing that here mu s, it would be equal to gs mu v as spin magnetic moment divided by h cross. So this is the expression for the spin magnetic moment, that is mu s, and this is only due to the intrinsic or internal spin of the electron, and this is also known as intrinsic magnetic moment. Thank you.